Giant things in space fascinate us. The vast number of videos comparing the sizes of stars or the scales of the universe, which gather millions and millions of views, demonstrate this perfectly. And when we talk about hypothetical artificial objects, currently the largest human-made object in space is the International Space Station. Its length is 109 meters or over 350 feet. It's about the size of a football field. However, science fiction can fulfill our need for gigantic space objects. I have spent quite some time looking at posters comparing the sizes of ships from different sci-fi movies, shows, etc. There are plenty of such videos as well. Starships the size of a city. And that's certainly not the limit. Take the obvious example of the Death Star, especially the second one, which is about the size of a decent asteroid. And don't get me started on gunmen the size of half of the observable universe, because for them to actually work you'd essentially need magic that allows to break the laws of physics. However, sometimes you can read about giant artificial space structures not only in sci-fi, but also in scientific literature, and there are even attempts to detect them through observations. I'm of course talking about megastructures like various types of Dyson spheres. Hypothetical structures around stars in the form of spheres, rings, or swarms of individual segments designed to collect the star's energy. But here's the question: why would you need so much energy? And here, there are a couple of interesting ideas. For example, this immense amount of energy could be directed towards computing. You could create a gigantic supercomputer on a stellar scale. This concept is called the Matryoshka Brain. Matryoshka is the other name for a Russian nesting doll. There is also a version of this idea called the Jupiter Brain. You could also use this energy to travel the galaxy. You could construct what's called a stellar engine, a megastructure that would allow for the movement of stars and planetary systems. But is any of this possible? Clearly not right now, but maybe in the future. How could it be done? Perhaps more advanced civilizations, well, if they exist, surpassing us by millions of years in development, have already built something like this and we might be able to detect it. Let's talk about all this today. I'm Andrei, and this is Cosmos Elementary. When humans first flew to the moon in 1969, NASA used computers like these. But aboard the Apollo spacecraft, instead of large cabinets, there were more compact onboard control computers used for calculations, navigation, and control. For its time, it was a groundbreaking technology, and home computers with comparable power only appeared about 10 years later. Today, even though it's not entirely possible to directly compare the performance of a modern-day smartphone to a specialized device like Apollo onboard computer, still, in some ways this is millions of times more powerful than computers that help get humans to the moon. The fact that in just a few decades computational power has increased by orders of magnitude, while energy efficiency has improved and everything has become smaller, is quite remarkable. Although supercomputers still can occupy entire floors of buildings. But what if it's not a floor, not a building, but a computer the size of an entire planet or even a star? Can you imagine what a supercomputer of that size would be capable of? Of course, it would answer the ultimate question of life, the universe, and everything. But seriously, it's hard even to imagine what kind of calculations such a computer would be capable of. People speculate about using these massive machines to create truly intelligent artificial intelligence, like in Dan Simmons' books, where AI quickly surpassed human development, started to invent technologies that humans hadn't even thought of. Such AI, of course, wouldn't rise against its creators. No. One could run super complex and detailed simulations, for example, for science, to better understand the structure of the universe. If it turned out that such a computer could be actually created, proponents of the idea that we live in a computer simulation would be thrilled. But is this possible? The concept of the Matryoshka Brain, a giant stellar computer, was introduced by Robert J. Bradbury. He came up with this concept in 1997, and it is most thoroughly described in this article of his. Unlike the vast majority of papers that I use as sources for my videos, this paper has not been peer-reviewed or published in a scientific journal, which Bradbury himself mentions on the very first page. One of the ways to improve silicon computer chips has been the constant production of transistor sizes. Today you can find chips, for instance, using a 3nm process. However, how this size is measured is a separate question. In any case, we are already not that far from the approximate size of a single silicon atom, which is 0.2 nanometers. It is possible that soon we won't be able to continue reducing the size any further or cram more transistors on a single chip. At some point, we are likely to hit the limits of quantum physics, and at such scales, quantum effects will start to take hold and classical processors will no longer be able to operate stably and predictably. There is, of course, the path of quantum computers, but that's a whole separate story. So, it seems quite logical to consider going in the opposite direction, towards increasing the size, but not of the transistors, rather of the computer itself. First of all, why is the concept called the Matryoshka Brain? Well, brain makes sense. It is a computer, especially if we're talking about artificial intelligence, but why Matryoshka, or a nesting doll? Essentially, the Matryoshka Brain concept is a variation on the Dyson sphere idea. It is a megastructure built around a star. I should remind you that the original version proposed by Dyson, where a solid sphere completely encloses a star, is likely impossible. A monolithic structure of such size would probably be unstable and wouldn't withstand the effects of tidal forces and rotation. But a system of rings or a swarm of individual segments is already more realistic. In the case of the Matryoshka Brain, rings could be also used. The key idea is that the structure should consist of separate layers, each positioned at progressively greater distances from the star. Each of the shells should consist of several key components. The surface facing the star would use radiation to generate electricity. This energy would then power the computer equipment, processors, memory, and so on. Next, we would definitely need to find a good cooling solution. The inner layers in particular could get quite hot due to their proximity to the star, and as we know, computers tend to generate a lot of heat as well. The fourth crucial component is radiation protection. High-energy cosmic particles can damage micro and nanoelectronics. Multiple layers are needed to prevent losing valuable energy into space. The inner layer absorbs the star's radiation, the radiators of this layer re-emit thermal radiation, which can then be captured by the next layer, and so on. Here's an illustration from the Bradbury's paper. It depicts the Matryoshka Brain in the process of construction. The final structure is meant to completely enclose the star to ensure that no energy is lost. The rings of individual shells consist of hexagonal segments. On this side there are solar panels, here is the computer equipment, and on the opposite side there are radiators. It is important to consider that the layers closer to the star must withstand higher temperatures, so suitable materials capable of enduring these conditions would need to be selected. The paper also suggests that in addition to the option with the star at the center, similar structures could be built not around the star, but by directing energy beams from other stars. Alternatively, a Matryoshka Brain could be constructed with its own power source, such as a nuclear fusion reactor. The fact that we don't yet have efficient nuclear fusion reactors should worry us the least, considering that we would need to use half of the solar system to build a Matryoshka Brain. So how do we make this happen? How do we actually get so much material for construction? So much of what I'm about to say sounds almost like science fiction, or completely like science fiction, at least for us with our current capabilities. It doesn't mean it's completely physically impossible, but for now it is beyond our reach, and it's hard to say whether it will ever become achievable. But still, this isn't something like, let's say, traveling back in time. But we could at least try to imagine such a civilization that would be able to achieve something like this. Bradbury uses the solar system as an example. First of all, we're limited by the amount of the material available. For the complete structure, a whole range of different materials would likely be required. If we look at the distribution of chemical elements in the solar system, it largely mirrors the composition across the universe. Almost all of the mass is in hydrogen and helium, with all of the heavier elements making up only a small fraction. Nevertheless, in numerical values, the amount of different materials available for construction is still substantial. Take, for example, processors. If we use modern chips as an example, the base material here is silicon. Silicon makes up a significant portion of the mass of rocky planets and asteroids. But in addition to silicon, materials like iron, aluminum, phosphorus, titanium, copper, gold, and many others might be needed. It is difficult to say exactly, because we don't have a detailed design of a megastructure, and we don't know precisely how much of each substance would be required, so we can only make rough estimates. Robert Bradbury writes that there may be enough material in the solar system to build such a megacomputer. The second question is, how exactly something like this could be constructed? The article proposes using robots to construct the Matryoshka Brain, and it also mentions von Neumann's self-replicating machines. The famous mathematician and physicist described such a hypothetical technology in his theory of self-reproducing automata. Such self-replicating factories, creating themselves from available materials, could significantly speed up the process, although they are not strictly necessary. Of course, an energy source is also required, not only for the operation of the computer, but also for its construction. Therefore, in the first stage, one scenario suggests the following. To start, the idea is to dismantle an asteroid several kilometers in diameter. From its materials, we could build solar panels, providing a powerful energy source to be used in the next phase. Then we would deliver this energy, perhaps using a focused beam, which is theoretically possible, to Mercury. What are we going to do on Mercury? That's right, dismantle it piece by piece. The materials from Mercury could be used to create many solar energy collectors, which would capture a significant portion of the radiation from our star. At this stage, the available energy would increase many times over. This energy could then be used to further dismantle asteroids, comets, dwarf planets, and moons of gas giants. The materials gathered from these sources might provide enough raw material to construct a significant portion of the Matryoshka Brain. In Bradbury's scenario, all these stages happen relatively quickly, assuming a high level of technological development and the presence of self-replicating factories. It's conceivable that this process could be completed within a few decades. It certainly sounds very bold. A slightly different scenario skips the first step with an asteroid. Instead, it suggests starting by dismantling Mercury and possibly parts of Venus. If all of this seems extreme to you, well, you haven't heard everything yet. There's also an option to dismantle giant planets. However, to do this, additional energy sources would need to be built nearby. Probably nuclear fusion reactors, and even in these fantastical hypothetical scenarios, it would take hundreds of years to accomplish. Naturally, all of this is still speculation, and at each stage there are many nuances. One of the problems that starts to arise on such a gigantic scale is signal delay. The maximum speed at which information can be transmitted is the speed of light. We even sometimes refer to it as the speed of information. At such scales, one part of the brain might be at the distance of Mercury, and another near Saturn or even Neptune. The signal could take hours to travel. This could indeed be a problem, although it depends on the task we are performing. Nowadays, we have an example of how computational power can be increased while the parts of the system performing the calculations are scattered across the world. I think some of you might have already guessed what I'm referring to: distributed computing. When a large number of separate computers work as a single system and work on the same task. Computers can be scattered across the world working in parallel, with each solving its part of the task. Perhaps some of you even participated in similar projects. I'm referring to SETI at Home project, where people could share part of their home computer's processing power to help analyze data from radio telescopes in the search for potential signals from extraterrestrial civilizations. Unfortunately, SETI at Home is no longer distributing new tasks as of now. However, you can still participate in another cool project, Folding at Home, where the folding of protein molecules is modeled. This could help understand the causes of many serious diseases in the future. In general, if the Matryoshka Brain performs calculations in parts, then the delay might not be the problem. However, if it is intended to be used for the work of a superintelligence in real time, that's where the questions arise. By the way, electrical signals in our brain and nervous system travel far slower than the speed of light. In some cases, it's only a couple of 100 kilometers per hour. However, there is still a way to minimize the potential problem with delays and, in general, make the whole concept more realistic. Though, of course, this will still sound like science fiction, just a bit less extreme. I'm talking about a concept called Jupiter Brain. The general idea is similar to what we've already discussed, a gigantic supercomputer in space, but as you can guess from the name, it is smaller in size. This idea was detailed by Andreas Sandberg back in 1999 in his paper The Physics of Information Processing, Superobjects, Daily Life Among Jupiter Brains. Many of the ideas here are reminiscent of the Matryoshka Brain concept. It could also be a gigantic supercomputer composed of separate segments. The material for building the megastructure could be taken from asteroids, moons, and even planets. A significant difference is that here it won't be possible to use a star as an energy source in the same way as it was with the Matryoshka Brain. Therefore, it is suggested to use nuclear fusion reactors here again. However, with smaller size, constructing such a system would be easier. It's not even necessary to build an object the size of Jupiter. You could create structure just a few tens of thousands of kilometers in diameter, and it would still have computational power far beyond anything we can imagine. It would be comparable in size to Earth, and the delays would be similar to those in existing distributed computing systems. Of course, parallel computing could also be used. Well, it is certainly interesting to speculate about such things, but as I've said before, we are still far from creating something like this. But what if there is already a civilization far ahead of us in development, and they need such a computer? So they've either built or are building it. Could we detect it in some way? Broadly speaking, the situation here might resemble the story of Dyson spheres. If in some system a Matryoshka Brain is in the process of being built and it doesn't fully cover the star, or its configuration is such that it only partially obscures the star, the presence of such a megastructure could be indicated by periodic, very strong dimming of the star, which we wouldn't be able to explain with any natural causes. However, the fact that we can't find a natural explanation doesn't mean that there isn't one. One could search for unusual signals in infrared range, such as the excess heat produced by the computer, which would also be difficult to explain naturally. If someone ever undertakes a targeted systematic search for such structures, a number of factors could help narrow down the search area. And I'm not even talking about systems where the chances of life are higher. Specifically, it would be more reasonable to build stellar computers not around just any star. For example, around a massive star whose lifespan is only tens of millions or even just a few million years. It wouldn't make much sense to invest so much effort and resources, only for the star to eventually explode as a supernova and destroy everything. Therefore, it would make much more sense to search around less massive stars, whose lifespan is longer. In general, this story aligns with the search for extraterrestrial life. Well, alright, computers are great, but what about riding the stars? Our Sun, like other stars, is a wonderful source of energy. And of course, it's a bit disappointing that almost all of this energy right now is basically wasted. We've already come up with one option, which is computations, and the second option is to use this energy for propulsion. I once made a video about another pretty crazy idea, building a starship out of an entire planet. Today we take a step up the ladder of crazy ideas and talk about not just moving a single planet, but an entire star. And by extension, since we're moving the star, all the gravitationally bound objects would travel with it as well. Planets with their moons and so on. These concepts are called stellar engines. And interestingly, unlike the previous idea, there are already a number of papers on this topic that have been published in peer-reviewed journals. Given that it would clearly require incredible engineering efforts, a legitimate question arises. Why would anyone need to move an entire planetary system? In the case of a planet starship, one possible reason could be the planet star, which is on the brink of dying. But the danger could also come from beyond the system. For example, another star might approach it too closely. In the history of our solar system, this has happened before, and a passing star could destabilize certain objects, such as sending comets from the Oort cloud into the center of the solar system. If the star gets even closer, the consequences could be far more dramatic. Another potential threat could be the explosion of a star nearby. It is generally believed that during the course of life on Earth, supernovae have erupted close enough to potentially impact life. Supernovae may have even contributed to some mass extinction events. And again, if such an explosion happens even closer, it wouldn't be too crazy to imagine that a more advanced civilization would have sufficiently accurate methods for predicting supernova eruptions, with a precise map of surrounding stars, and could predict their position in the future. We can already do this to a certain extent today. Now imagine you find that in, let's say, 100,000 years, a star will approach your home system and then explode as a supernova, or perhaps it's already close enough, and the explosion will destroy life on the planet. Another danger could come from a cloud of matter along the system's path through the galaxy. You have some time to act, and the chance to do something about it, like attempting an evacuation. Not everyone could fit on starships, and there wouldn't be much space. The idea with the planet starship is certainly interesting, but it's always more pleasant when there is sun in the sky. So why settle for less? Why not fly away, not just with the planet, but with the star as well? Can this be done? At least in theory. In literature, you can find a couple of interesting options. Authors Viorel Badescu and Richard Cathcart propose a classification of stellar engines with three main types: A, B, and C, and later they added the type D. I should mention right away that not every stellar engine is designed specifically for moving a star. Type A is a stellar engine in which the radiation from a star is used to create thrust. The main example here is the Shkadov drive, proposed by Leonid Shkadov. Here is how the concept is generally described in the various articles I've come across. On one side of the Sun, a giant parabolic mirror is placed. This creates a symmetry which generates thrust, causing the Sun, along with all the planets, to slowly begin accelerating. When I read such explanations, I already know that if I simply repeat them verbatim, many of you will have questions like, where does the thrust even come from? After all, we didn't exactly attach the mirror to the star with cables to create a solar sail of unimaginable scale. The mirror is just floating separately. But in many explanations I found, either nothing beyond the general description is clarified, or I've even come across explanations that are just outright incorrect. For example, on one website I came across a claim that photons reflected from the mirror return to the star, pushing it. But that's not quite accurate. If anything, the mirror should redirect radiation away from the star, and here is the thing. First, we know that the light can cause objects to move. I made an entire video about drives that use light for propulsion. The most well-known concept is the solar sail or light sail, where photons transfer momentum to the sail, effectively pushing it and causing the spacecraft to move. In the same video about photon propulsion systems, I said that if we place a flashlight in space, far from massive objects, and turn it on, the photons emitted from one side would generate thrust. This works due to the law of conservation of momentum. Photons travel in one direction, then the flashlight moves in the opposite direction. It is similar to a rocket engine, except instead of matter, it's light. The Sun, under normal conditions, emits radiation approximately evenly in all directions. The momentum carried away by photons in one direction is balanced out by photons emitted in the opposite direction. And as a result, there is no net movement. The Sun predictably continues its orbit around the center of the galaxy. But if we create a symmetry in this radiation, well, we naturally can't just turn off half of the Sun. This is where the giant mirror comes in. First, it needs to be placed in a static position relative to the Sun, meaning it doesn't move in orbit around it. It sounds difficult. Try to stop a planet, what would happen to it? It would fall onto the Sun. The orbital velocity is what prevents planets from falling into the Sun's gravitational well. But, as we know, the Sun's light exerts a certain pressure and pushes matter away from it. You can try to find a balance between the Sun's gravitational pull and the pressure of its light. Make the mirror thin enough, calculate everything correctly, and it could remain in a stable position for a very long time. At this point, it might still be unclear how a symmetry is created, since radiation is still leaving the Sun in all directions. It's just that some of it gets reflected, but the Sun doesn't really care about that. And in one of the articles by Badescu and Cathcart, there is an important clarification that answers this question.
Here's the quote. The mirror is situated such that the central symmetry of the solar radiation in the combined mirror-sun system is violated, and as a consequence, a certain thrust force will arise.
And the key here is the mirror-sun system. Although the mirror is not attached to the sun by some kind of tether, like a cell to the spacecraft, they are gravitationally bound, with the mirror remaining at a constant distance. They act as one system, and when the mirror reflects some of the light in one direction, a symmetry in the light pressure is created across the whole system. As a result, we get a non-zero acceleration in one direction. It is somewhat similar to my flashlight example, but instead of the flashlight, it's the mirror-sun system. The acceleration will be very weak, but over time, the star and the entire system together could reach significant speeds. There are estimates that a stellar engine could eventually accelerate the system to even 1% of the speed of light. Of course, it could take millions and millions of years. Also, with the Shkadov drive, it is better to place it over the poles of the star. If it is placed near the equator, it could end up focusing additional radiation towards the planets, which might not be very pleasant. That was Class A. Class B stellar engines don't generate thrust, instead the star's energy is used for performing some kind of work. Class C combines first two classes. Here stellar radiation can be used both for movement and as energy source.
They also mentioned Type D. Here, again, the focus is on movement, but instead of utilizing radiation of the star, its material is used.
This is called a star tug, and this concept is described, for example, in this paper. Here is a diagram of how this should work. On the one side, a mechanism is placed that can siphon material from the star. Then this mass is accelerated and ejected in the opposite direction. This counteracts the star's gravitational pull, creates thrust, and again moves the entire system. There are estimates that such a system could accelerate up to 27% of the speed of light, though over several billion years. But if we don't aim for such a high speed, within 1,000 years, such an engine could make the star's orbit and the entire system's orbit retrograde, meaning it would start moving in the opposite direction to the motion of other stars in the galaxy along their orbits. This in turn could accelerate the process of colonizing other systems. And what if someone has already created something like that? Is it possible to detect this? There are papers on this topic as well. One way to find a stellar engine is by its anomalous speed. If a stellar engine accelerates to speeds close to the maximum, and if we observe a star moving at abnormally high speeds, which is difficult to explain through natural processes, then at the very least it would be worth taking a closer look. Here's another paper. It proposes an interesting idea: how we could potentially detect Shkadov drives if they are flying through the galaxy using planetary transits. The light curve of transits, when a planet passes in front of the star's disk and temporarily blocks part of its light, have a characteristic shape. It looks like this. They are usually symmetrical, with the left and right sides of the dip in the curve being mirror images of each other. But what if a planet passes in front of a star, part of which is hidden by a giant mirror? For example, this is how the stars might appear to an observer on Earth, a truncated disk. Accordingly, this would also be reflected in the light curve, and it could look like this. Therefore, if we find such an unusual light curve of a star, it could potentially indicate the presence of a megastructure around it. It is fascinating to sometimes ponder such large-scale technologies that are currently beyond our capabilities, especially if there is even the slightest chance that they already exist somewhere, and we might be able to find them.
Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoy my videos, please like, comment, subscribe for more videos in future, and share it with your friends, family, and whoever might like them. Thank you for watching. Bye.